Morning children. Today we will learn about the conductance of electrolytic solution. As we know, there are two types of conductors. One is metallic conductor and another is electrolytic conductor. In case of electrolytic conductor, there the conduction is by means of ions. So they are also called as ionic conductors. So actually the electrolytes are two types. One is a strong electrolyte and another is weak electrolyte. Strong electrolytes are those electrolytes which when kept in water undergoes nearly 100% dissociation and their conductance is larger. Weak electrolyte undergoes partial dissociation in water and their conductance is lesser, like acetic acid, HCN, H2CO3. These are weak electrolytes. Now factors affecting electrolytic conduction. So these are the factors. Nature of electrolyte. Nature of electrolyte means whether it is weak electrolyte or strong electrolyte. Size of ion. Smaller the size of ion, greater will be its conductance. As you know that when we take the ions in the medium, so ions are stabilized by solvation effect. So as you know that the size of lithium ion in alkali metal is largest. The size of hydrated lithium ion is largest in the medium, so their conductance will be lesser. So larger the size of ion, lesser will be its conductance. Nature of solvent. This involves the solvent-solvent interaction, that is viscosity. So if the solvent will be more viscous, then the movement of ion will be slow and conductance will be lesser. Concentration of solution. If the solution is more concentrated, then अगर ये weak electrolyte है, so there will be less ions formed because dissociation will be lesser. And if it is a strong electrolyte, then the attraction between the ion will be stronger, so their movement will be lesser, so the conductance will be lesser in case of concentrated solution. Now temperature. If we increase the temperature, then the conductance of electrolytic conductor increases because this loosen different types of interactions like solute-solute interaction, solute-solvent interaction and solvent-solvent interactions. Now we will take certain terms like resistance. Obstruction to the flow of current is called as resistance. Now Ohm's law. Potential difference across the conductor is directly proportional to the current flowing through it at constant temperature. V is directly proportional to I. Sometimes V is represented as E. Potential difference is represented by E. So E is directly proportional to I. So and B will be equal to Ri, where R is proportionality constant and it is the ratio of potential difference to the current flowing through the conductor. Its unit will be, potential difference is measured in volt and current in ampere. So volt per ampere or ohm. Conductance. Ease of flow of current is called conductance. It is defined as the reciprocal of resistance. It is represented either by C or by G. So G equal to 1 upon R or C equal to 1 upon R, and its unit will be ohm inverse, mho, omega inverse, or it is also called as Simon. 1 Simon equal to 1 omega inverse. Now specific resistance. This is also called as resistivity. The resistance of any conductor is directly proportional to its length, and the resistance is inversely proportional to its area of cross section. So this R will be equal to rho L by A, where rho is the proportionality constant and it is called a specific resistance. So what is this specific resistance or resistivity? A specific resistance is defined as the resistance which is offered by a conductor whose length is 1 centimeter and area of cross section is 1 centimeter square. Or we can define the resistivity is the resistance of 1 centimeter cube of the conductor, that is whose length is 1 centimeter and area is 1 centimeter square. So rho equal to Ra by L. Now its unit. Resistance is measured in omega and area a centimeter square and length in terms of centimeter. So this will be centimeter, omega centimeter or ohm centimeter. Now specific conductance. Reciprocal of specific resistance is called specific conductance, or it is also called as conductivity. It is denoted by kappa. Kappa equal to 1 upon rho, and if we put the value of rho, then it is equal to 1 upon r L by A, where so the kappa will be equal to 1 upon r L by A, and this 1 upon r is also called as conductance, and this L by A is called as cell constant. So sometimes 1 upon r is represented as G and L by A is represented as G star. So kappa is equal to G into G star, where G is conductance, that is 1 upon r, and G star is a cell constant in which the electrolytic solution is kept. So G star, that is cell constant, it is equal to L by A. Now what is kappa? A specific conductance is the conductance of 1 centimeter cube of the material whose length is 1 centimeter and area of cross section is 1 centimeter square. Now if we take another term, that is molar conductivity, it is the conducting power of solution containing 1 gram mole of electrolyte. So such that the 1 mole electrolyte is completely dissociated in the medium. It is denoted as lambda m. So it is the conducting power of all the ions produced from 1 gram mole of electrolyte. Now lambda m is equal to kappa into B, where kappa is a specific conductance, and what is V? V is the volume of solution containing 1 gram mole of electrolyte. What is V? Volume of solution containing 1 gram mole of electrolyte. Now suppose if the molarity of solution is capital M, so what does it mean? That m gram moles of the electrolyte solute is present in 1 liter, that is 1000 centimeter cube of the solution. So if we find out what is the volume which contain 1 gram mole, so this will be 1000 upon m centimeter cube. So this is actually the volume which contains 1 gram mole, and we know that the volume of solution containing 1 gram mole is called as V. So 1000 upon m will be equal to V. So now if you substitute this value of V here in this expression, so lambda m will be equal to kappa into 1000 upon molarity. Now unit of molar conductivity. As we know, lambda m equal to kappa into 1000 upon molarity. Molarity means mole of solute upon volume of solution in liter, that is 1000 centimeter cube. So kappa unit is ohm inverse centimeter inverse, and 1000 is in terms of centimeter cube, that is 1000 ml of solution upon mole. So this will be equal to omega inverse centimeter square per mole, or it is Simon centimeter square per mole. So this is the unit of molar conductivity. Sometimes it is asked in 1 mark question, what is the unit of molar conductivity? So it is omega inverse centimeter square per mole or Simon centimeter square per mole. Now we will take one question. The conductivity of a solution containing 1 gram of anhydrous BaCl2 in 200 centimeter cube of solution has been found to be 0.0058 Simon per centimeter. What is the molar conductivity of solution? एटॉमिक मास दिया हुआ है, तो सबसे पहले हम गिवन लिखते हैं. WB 1 ग्राम है, मोलर मास 208 ग्राम पर मोल है, वॉल्यूम ऑफ सॉल्यूशन 200 ml है. तो सबसे पहले हम मोलरिटी फाइंड आउट करेंगे. मोलरिटी क्या होगा? नंबर ऑफ मोल्स in 1 liter of solution. So it is comes out 0.0240 mole per liter. Now if we keep the value in the formula of molar conductivity, lambda m equal to kappa into 1000 upon molarity. So kappa is given, it is 0.0058 into 1000 upon molarity is 0.024. So on solving you will get 241.67 Siemens centimeter square per mole. This is the answer. Now the topic is how to measure the conductance of any electrolytic solution. So as we know that the conductance of any conductor can be obtained if we can measure the resistance of the conductor, because the conductance that is G or C is the reciprocal of resistance. So now the resistance of any conductor is measured by simple bridge method, that is called as Wheatstone bridge method. In this method, 4 resistances are connected in a specific sequence, as R1 is connected to R2, R3 and R3 is connected to R4, and then these are connected here. Now the bridge is made like this, and between these 2 points, suppose this is point A, B and here C and D. So between A and C we attach the galvanometer, and B and D are attached with the source of here. As you see, DC current is used. Now so this bridge is used. Now at the null point in the detector are here in galvanometer, the ratio of R1 to R2 is equal to R3 to R4. Now see, in this case R3 R4 are fixed, R2 is our unknown resistance which is to be measured, and R1 is variable. तो हम यहाँ डिफरेंट रेजिस्टेंसेस को अलग अलग बार ट्राई करते हैं और हम डिटेक्टर में देखते हैं कि नल पॉइंट कब आता है. तो नल पॉइंट पर R1 टू R2 रेशियो जो है वो R3 टू R4 के बराबर हो जाता है. नाउ फ्रॉम हियर वी कैन मेजर आवर अननोन रेजिस्टेंस, दैट इज R2. R2 is our unknown resistance. So in this way it can be measured, and then we can measure the conductance. But the problem comes when we measure the conductance of any solution, because solution cannot be connected just as we connect any wire or metallic conductor. So the solution R2, that is unknown resistance, it is replaced by conductivity cell which contain the electrolytic solution whose resistance is to be measured. So ध्यान रहे कि इसमें हमें कुछ चेंजेस करने पड़ेंगे. R2 को हम उस कंडक्टिविटी सेल से रिप्लेस करेंगे जिसमें कि हमारा इलेक्ट्रोलाइटिक सॉल्यूशन होगा. दूसरा प्रॉब्लम आएगी कि यहाँ पर जो DC सोर्स है, अगर हम DC सोर्स यूज करेंगे और इलेक्ट्रोलाइट सॉल्यूशन यूज कर रहे हैं तो वहाँ पर इलेक्ट्रोलाइसिस होने लगेगी, पोलराइजेशन होने लगेगा. तो ऐसे कंडीशन में जो सोर्स ऑफ DC है इसको हम अल्टरनेटिंग करंट ऑफ फ्रीक्वेंसी रेंज 550 टू 5000 साइकिल पर सेकंड से रिप्लेस करेंगे. दूसरी प्रॉब्लम ये आएगी कि जो गैल्वेनोमीटर है इसको हम ईयरफोन से रिप्लेस करेंगे, और जब हम ये तीनों अरेंजमेंट चेंज कर देंगे देन एट द नल पॉइंट द same ratio will exist, that is the R1 to R2 equal to R3 to R4, and R2 can be determined. So in this way we can determine the resistance of electrolytic solution taken, and once the resistance is known we can measure the conductance, and also we can measure the kappa, because we know that kappa equal to 1 upon R L by A. So what conductivity cell we have taken, it will have a definite value of cell constant. Since the resistance is measured from here by Wheatstone bridge method, R2 is our unknown resistance, so kappa can be determined. And once the kappa is determined, so we can determine the molar conductivity also, because molar conductivity equal to kappa into 1000 upon molarity of the solution. So in this way we can measure all this. Thank you.